In this tutorial, I show how to perform simulations of OLED using ZFOS. So I'll start with an optical simulation, and while one can load many examples of such a simulation from the ZFOS database, I will here start from scratch. So I use new simulation, which creates a default layer stack, and I then can specify the layout of my OLED stack. And I start adding some more layers. So the surrounding is air. And then there's the glass substrate of 500 microns thickness. And then the ITO top electrode, the APC hole transport layer, the emission layer, and an electron transport layer, which here is LQ3. And then finally, the aluminum bottom electrode. Now, as I said, we will first perform an optical simulation, and for that purpose, I have to enable the emission module here. And then I have to provide optical material data for the different layers. So for the glass, I use a constant refractive index of 1.5, and it's treated as non-absorbing, so the extinction coefficient is 0, and the layer is treated as incoherent as it is much thicker than the wavelength of the light. For the other layers, I load the NK data from files in the database of ZFOS. So I navigate to the respective NK files for all the different materials. This comes with a very extensive database for all kind of OLED and also OPV materials and electrode materials. But of course, the user can also specify his own measured or data taken from literature. Okay, next we have to specify the emitter. So we enable here emitter in the emission layer. And now we have to give the emission file. So this is the intrinsic photoluminescence spectrum. And we use this ARPPY3 spectrum. And then we have to specify the distribution of the emitting dipoles. We use here a delta distribution in the center of the emitter layer. At the custom dipole orientation, the conversion efficiency is set to 1, so a phosphorescent device, and the quantum efficiency 0.9. Now we can rename simulation to something like OLED optical. This is very fast. We immediately see here this bright green that is emitted. But we can also check the performance parameters in the key figures, like luminance, current efficiency, luminous efficacy, or the EQE assuming a Lambertian angular distribution of the emission, because so far we did not specify any angles, so this is done at normal emission angle. Of course, the exciton density is the delta distribution that we specified. And if we now look at the emission spectrum, we can directly compare it to the intrinsic PL spectrum and see that there is some deviation in the spectral shape due to the impact of the cavity or the layer stack. So now we can start looking into the impact of the different stack design parameters. So for instance, thickness of the ETF. And to do this parameter variation, I enable the sweep mode. So this is the mode where you can do parameter variations. So now I check here the layer properties. So LQ thickness. I vary this from 1 to 141 nanometers in steps of 10 nanometers. We can rename again, ETL sweep, and run the simulation. Now, if we look at the emission, now as a function of wavelength and the ETL thickness, we can see that we have here a clear maximum. So this is the tuned, and in terms of color, we see that there is some shift from green to yellow when you go away from the tuned state. And this maximum can also be found in the radians. And in order to investigate this further, we can do a modal analysis. So in the emission settings, so far we use the spectral mode, which is the default. We can go to mode analysis. And then look at the different loss channels where the emitted power, and since it's a bit longer, I performed this simulation already. And so we can directly look at the result. For instance, the stacked average contributions. And so here you have the different contributions to the power loss, and in red is the outcoupled part. And indeed, we have the maximum of this contribution at around 60 nanometers. But there is a lot of loss from different contributions, for instance, substrate guided or absorption loss, guided modes, and a very important part for evanescent decoupled, and some small non-radiative loss. So we now come to the full optoelectronic simulations of the OLED. So we use the same layer stack, but now we consider also transport of charge carriers and excitons. In order to do that, I have to enable the diffusion module here in addition to the emission. And this means that I also have to specify electronic properties, starting with the electrodes. So I set here the ITO as electrode, and I have to specify boundary conditions. In this case, thermionic with a work function of 5.1. And then here, the aluminium with the bottom electrode at the work function of 3.3. Okay, and the layers in between now have to be set as semiconducting. And again, I have to provide material data, in this case, electrical material data. And I can also import this from files, the .em files in this case. So for the Q3, for the emission layer, and for the whole transport layer. Okay, so now I have here all the electrical material properties that I need for the diffusion simulation. So HOMO-LUMO levels, effective density of states, directly constant, but also the mobilities of electrons and holes, which here are given in a constant mobility model. Now I can go to my emitter properties and change the distribution of the dipoles to exciton coupled. So we use the actual exciton distribution. So we have to now specify the excitons. And for that, I go to semiconducting here. And I have to enable the excitons and add exciton population with properties like the radiative decay. So I choose 1 per nanosecond and the generation efficiency of 1 again. So now the generation efficiency is specified in the exciton properties. And so now I can use this exciton. Well, it's already automatically taken because it's the only one. And so the emission is now coupled to the exciton properties. Okay, now I have to also set the bias voltage at which the emission is computed, and well, actually the whole drift diffusion problem is solved. And we'll also specify some solver settings for the drift diffusion run. Then I rename to full. So check again. Okay. Now this was also very fast. And we see we still have this nice green color, which can also be seen from the color diagram. But now we have, in addition to the optical properties, we have some electronic properties. For instance, we can now look at the actual exciton profile, and we find that it looks, well, not very much like the one we specified in the optical simulation, but we have something like a split emission zone, so the exciton density accumulates at the boundaries of the emission layer. And now, so this was at one bias voltage. We can now compute the full current voltage characteristics using, again, a sweep. So I enable here this sweep and set voltage as the sweep parameter. Sweep from 1 to 5 volts instead of 0.2 volts. Okay, and then we, from the currents, we find this current voltage characteristics with here. We can also sweep now different electrical parameters of the structure to which we have now access. So we can replace, for instance, this sweep over voltage by a sweep over the exciton properties. So I choose here the electrical material properties of the emitter, the exciton, and for instance, sweep the non-radiative decay rate. So this was 0 so far, and I can, for instance, sweep it from 10 to the minus 4 to 1 per nanosecond. So this corresponds then to the radiative lifetime. And I do this in a log mode, so 1 per decade. Okay, the current of course does not change, but if we look at the internal quantum efficiency now, there is a drastic decrease of this performance parameter when approaching the radiative lifetime with the non-radiative. We can also sweep electrical properties, so not excitonic but electronic quantities. So for instance, sweeping over the mobility of the electrons in the ETL. So here I choose the ETL layer, and then in the electrical materials, the mobility from a very low mobility to a rather high mobility. Also in a log scale. And again, we find a drastic impact to internal quantum efficiency, but also on other performance parameters such as the luminance.